The intention of this lab was to measure data collected from an observation of an object with constant velocity. The information from this observation, including time interval of motion as well as initial velocity, was used when creating a computer simulation of the moving object. This computer simulation allowed for the prediction of motion and change in position of a rolling ping pong ball by using physics concepts like Newton's first law and the formula for motion prediction with a constant velocity. The observed motion was recorded using an iPhone and analyzed using the tracker application. Measures were taken to eliminate possible error, including assurance of proper lighting, limiting roll of the ball that may be perpendicular to the line of recording, and maintenance of an axis throughout by working to remove camera shake. After recording and uploading the video of the rolling ping pong ball, the video was uploaded into Tracker where an axis was set in alignment with the motion of the ball. The frames per second were set to those of an iPhone camera, which was found to be 30 frames per second, and the distance was calibrated using a calibration stick. The calibration stick was used to measure the diameter of the ping pong ball, which was a known measurement of 38 millimeters. The motion of the ball was recorded in every video frame through the placement of markers on the center of mass of the ping pong ball. This allowed for the production of a displacement versus time graph. After creating a displacement versus time graph using the observed motion, I used GlowScript to simulate the motion of the ball given there was no net force acting on the ball, and it began with the same initial velocity as the ping pong ball recorded in the video. In the code, I changed the mass and size of the ball to fit the size of the ping pong ball. However, because this lab allows for the assumption of no net force, these measurements will not change the outcome of the displacement versus time graph created by the program. To find the initial velocity of the ball, I used the first two displacement measurements from the observation video and calculated the change in displacement over change in time, which was found to be 0.513 meters per second. These values were inputted into the ball's velocity, and initial position of the ball was set to be at the origin. Additionally, the parameter of the time step was set to be 0.034 seconds. This program utilizes a while loop which iterates the time by this time step, which is the same amount of time between frames in the tracker program. Each time it iterates through this while loop until reaching the time of 1.733 seconds, which is when the clip ends. The position of the ball is updated using the formula R equals R plus velocity times delta t, where the value of R is updated during every iteration. The formula resulted in the dataset here. Both datasets from the observed and calculated values of the displacement of the ball over time are plotted in this Google Doc. In the graph comparison, it is evidence that there are differences in the simulated motion of the ping pong ball and the observed motion of the ball. One initial observation of the graph of the displacement versus time for the video compiled by Tracker is that it is concave down a bit throughout. This could be the result of a few things. The first could be that the ball rolls slightly backwards in the video, contributing to the illusion that the ball isn't rolling as far, when in actuality the ball's distance is being traveled, but it is being distributed among its X and Z components, the latter of which isn't captured in the videos and can't be incorporated in the Tracker application. Additionally, there's a possibility that there's friction occurring over this interval, which could decrease the rate of change in displacement over time. Another difference in the graphs is that we see the simulated version of the ball travels a bit further than the actual observed ball. This could be attributed to either the previous two reasons mentioned, or it could be because of the error and calibration stick in the Tracker app, not configuring the video to the correct measurements. All these reasons could contribute to a smaller measured displacement from the observed ball than the simulated ball. What if the axes were flipped in Tracker? It would be possible to invert the whole video and have the ball rolling from right to left instead of left to right. In that instance, the origin would be placed at the initial center of mass, and the rolling would be in the negative x direction. The resulting graph would be of the same slope but negated. The graph would be sloping down and to the right, beginning at the origin. To compensate for this in GlowScript, the initial velocity would be inputted as negative. In this model in GlowScript, we assume the net force to be 0, which would allow for constant velocity. The forces acting on the system include those of gravity and normal force. It is possible to calculate these forces using the formula F equals ma, where m is mass of the ping pong ball, which is 0.0027 kilograms, and the acceleration due to gravity is negative 9.8 meters per second squared. This results in a gravitational force of negative 0.026 newtons. The normal force is equal and is in the opposite direction. The force of friction is assumed to be 0 in this case.